Hello everyone, thank you for joining us here. My name is Minam and today we're going to be looking at electromagnets. So a few of our learning objectives are, and there are a few, to understand that moving charges generate a magnetic field, to be able to plot the magnetic field around a wire and a solenoid, to be able to recall that an electromagnet is a solenoid around a soft iron core, and to be able to describe how to increase the strength of an electromagnet. I know it sounds like a lot, but all we're doing is building on the knowledge we gained in our previous videos, as really we do with all of physics, so I'm sure you'll understand everything by the end of this video. Okay, so let's get started. The first thing that we need to understand is that moving charges, so electrons in a wire, generate a magnetic field around the actual wire itself. So here I have my wire, and let's just draw some electrons inside it, right? E minus, 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 etc. Okay, now I can see the I here, which stands for current, and this tells us direction of conventional current. Remember, conventional current goes from positive to negative, so that's what this I is talking about here. So we can see that the current is moving upwards, and it's generating this 3D magnetic field here, which is represented by these concentric circles. So concentric really means a circle within a circle, like that. Okay, so these are the field lines. And you can see that they sort of get wider apart. Like, this is not an excellent diagram, right? These are really meant to get really quite wide. The further away you get from the wire, that shows you that the field line density is decreasing, and so it shows you that the magnetic field strength is also decreasing the further away you get from the wire. And that's all makes sense, right? We expect it to be strongest right up close to the wire and then drop off the further away you get from it. Okay, but now we want to understand is that how do we actually work out the direction of the magnetic field, right? It's telling us that it's this way, right? And so that's anti-clockwise, right? So I had to work that out myself. But how do we actually understand that? Well, we use something called a right hand corkscrew rule. Okay, so you take your right hand, right, and then you do this, right? You give a thumbs up. Okay, now the direction that your thumb is in would be the direction that the current is flowing in. Okay, and the direction that your fingers curl around in tells you the direction that the magnetic field line is traveling in. Okay, so we can see here that current is going up, and so my fingers are curling around anti-clockwise, and so I can see here that the magnetic field is also traveling anti-clockwise. Okay, so that's just one straight wire, right? So this is a 3D view, but we can also have a look at it from a 2D view, which is really what you'll get in your exams. Okay, so here I have just a dot to represent my wire, then I have a few field lines. I'm only going to do 2 just to save a bit of time. Okay, now the first dilemma: which way is the wire going? Now, the way that I was taught this was to think about arrows. Okay, so if I have my arrow here, bit of a wonky arrow, right, and it has the fletching at the back. If an arrow was coming towards me, I would only be able to see the tip of it right here, right? So I would only see a tiny dot. So this dot tells you that the wire is coming out of the paper. So wire coming out of paper. Now, if I was to see an arrow moving away from me, I would only be able to see this little bit here, which would look like a cross. So if I had another diagram here which had a cross, yellow field lines all, this tells you that the wire is going into the paper. Wire going into paper. Okay, so let's look at the wire coming out of the paper first. Use my right hand. I point the wire towards my face, right? I can see that my hands are curling this way around, which ends up being that the magnetic field lines are traveling this way. Because remember, they have to flip every half turn, right? Because you go like that. So again, like that, like that, like that, and so on and so on and so on. Okay, so that's my first field. Now I have my wire pointing away from me, which is a little bit awkward, but I do that. I know it's pointing away. I can see my hands are curling this way around, so I do this way. Again, no more wonky field lines. Oh well, like that. And you can also see that the field lines have been reversed, and that makes sense, right? Because if we're talking about the same wire, one way it should be going one way and the other way should be going the other way. That doesn't make sense intuitively. Now that is just a single wire. Now we're going to have a look at an electromagnet which is made up of a solenoid, and a solenoid is nothing but just a curled wire. Okay, so now let's have a look at electromagnets and a solenoid. So what is a solenoid in of itself? So a solenoid is just a fancy engineering term for a coil of wire, usually copper. Why is it usually copper? Well, copper is an excellent conductor. So that's why we tend to use copper for coils of wire, right? And wire in general. Now, we can see that the electric current goes in here and it goes out of the loop of wire there. Now, if you remember earlier on in the video, I told you that when a current passes through a wire, a magnetic field is generated around the wire. Now, when we loop it up like this, all of those magnetic fields, they actually interfere with each other and they combine into this overall magnetic field you see here. Now, this shape looks very familiar, doesn't it, right? That's because this is just a normal magnetic field. So again, we have our north pole here and a south pole here. And also a very important thing is that if we were to reverse the polarity of the current, so if we were to say electric current out here and in there, these north and south poles would also flip, right? The polarity of the electromagnet, polarity of what? We're talking about solenoid right now. We'll move on to electromagnet soon. Polarity of solenoid depends on current flow. Okay, so where we have current in, that will be your north pole. Where we have current going out, that will be our south pole. Okay, and as always, we can also draw in our field lines, which, if you remember, always go from north to south. So we go do an arrow out there. We have arrows going out there, there, into south there, and so on and so on and so on. And we also have a uniform magnetic field inside the solenoid itself, just like we have a uniform magnetic field inside magnets themselves, right? If you remember, we had our bar magnet here, north, south, that it also had field lines inside the magnet itself. Okay, it's exactly the same with the solenoid. Now, those field lines inside, sure, they're kind of dense, right? But what if we could really collect them together in something else and make them even more dense? By, say, putting a soft iron nail inside. Okay, so now we've created an electromagnet. This is an electromagnet. Okay, so our iron nail here acts as sort of as to concentrate the magnetic field lines inside, right? And so now that you've concentrated those magnetic field lines, what happens to the strength of the magnetic field? Well, if we concentrate something, we sort of decrease the distance between adjacent things, right? So we increase field line density, and so our overall field strength increases, right? So we get a very strong magnetic field around the iron nail itself, and this is really an electromagnet. An electromagnet, all it really is a solenoid with a soft iron core inside of it. And it can be controlled with electricity, right? As long as the electricity is on, the wires have a current flowing through them. The dense iron core collects all of the magnetic fields of the wires, right? Of really the solenoid. It concentrates them and it causes a magnetic field to be induced. That is a very important word. So magnetic. Actually, let's do it in green. So actually, no, red. So it really sticks out. Magnetic field is induced. To induce something means to bring into, right? Around the soft iron core. Okay, as a result of current flowing through the wires. Okay, but as soon as we would say unplug the battery or flip the switch, all of that magnetic field would just simply disappear. So that's the real difference between a permanent magnet and an electromagnet. Electromagnets can be switched on and off, permanent magnets can't. Okay, so there are a couple of things we can do to increase or decrease the strength of this electromagnet. And we're going to have a look at those next. Okay, so there are three main ways you can increase the strength of an electromagnet. Number one, and so the most common one that you'll hear, right, is just increasing the number of turns in the actual solenoid itself. Now this makes sense because if you increase the number of turns, you get more magnetic fields produced around the wires, right? Because there are just more wires, right? So the overall magnetic field around the electromagnet becomes stronger because all of those little magnetic fields around each loop of the wire, right? They all add up. So if you have more loops of wire, you get more adding, you get a bigger overall field. So that's number one, increasing the number of turns. Number two, we can just increase the current. If we increase the current flowing through the actual wires itself, there are more electrons passing through the wire. Because remember, Q is equal to IT, right? That's charge is equal to current multiplied by time. So if we want current, we have Q over T, that equals I, right? So if we increase the current, so let's do that in a different color. So if we increase the current in the same amount of time, we get more charge flowing through the actual wire itself. Charge here is really shown by electrons. We have more electrons, we have a bigger overall magnetic field produced around each loop of the wire. So that's number two, increasing the current. Number three, and this is the one that people sort of forget, right, is actually having a bigger iron core, or if you didn't have an iron core in the first place, putting in an iron core, right? Because remember, the job of the iron core is to really combine all of the uniform magnetic fields inside the solenoid itself, and so sort of like expand it to increase the overall strength of the electromagnetic field, okay? So we can either make it bigger, or you might also hear sometimes called lamination, which is where you take sheets of iron, right? So let's do that, and you sort of glue all of these sheets together, sort of like one top of each other, right? And so that's called lamination. That's usually for transformers, but that's just a bit of extra information. So there are three main ways to increase strength of the electromagnet: increasing number of turns, increasing the current, or a bigger iron core. If you didn't have one in the first place, put in one. Now you understand everything you need to know about electromagnets for your GCSE.